Okay, I think we're all systems go. There are still a few people trickling in, but I would like to welcome you to the second Carbonate Forum. My name is Fiona Whittaker from the University of Bristol. I wish I could welcome you to sunny Bristol, but that'll have to wait. What I'd like to do is just introduce the conference briefly. So the Carbonate Forum was set up just over a year ago. It was supposed to be a real meeting where we all got together. Our aim was to bring together early career researchers to present their work. What we consider is that the early career researchers are often really at the forefront of scientific advances. They're custodians of these amazingly rich data sets. They're up to date with the current literature in ways that some of us struggle to be, and they have really cool ideas that can be tested. And what we wanted to do was set up a forum where we could discuss what early career researchers could present, and we could discuss this fundamental science. We wanted new ideas, new results, not a sort of conference presentation where everybody has the complete bottom line answer to everything, but really a forum for discussion. And in structuring and reviewing the abstracts, we've emphasized the importance of communicating the hypotheses, the scientific principles, and the concepts behind the work, rather than just focusing on final results and their application. So I'd just like to share a couple of slides with you. The first one is just about to come up. A summary, excuse me. Everyone else will be much more efficient than I am at doing this. There we go. Hopefully you can see that now. The first one is just a summary of, let's get rid of me. A summary of the conference we held last year. We hadn't planned, as I said, we hadn't planned for a virtual conference. We responded pretty quickly. So this was one of the, we were really at the forefront of virtual conferences, which have become standard nowadays. And as a result of that, we thought it was quite useful for us to review the outcomes of the conference. And what really excited us, first of all, was that so many of you dialed in. We had 466 participants. We had a large number of early career scientists, which was our first objective at the conference. A good mixture of academics, industry participants and other participants, and a good gender balance. We had participants from 56 different countries. Aside from the benefits in terms of the carbon footprint, we were just very excited that we could include so many people. I'd like to just say a few words of thanks to the other members of the scientific committee who have reviewed abstracts and given feedback to people. Stephen Lokier, Peter Burgess, Kathy Hollis and Rachel Wood, thank you very much. Thank you to our discussion leaders. We're introducing this year at the end of each day a forum discussion. There's a different topic on each day. And those discussions are meant to involve the audience, but will be led by different leaders. So we'll have Jean, Dave and Pete on day 1, and Sasha, Nick and Rachel on day 2. And I'd also like to thank our session chairs. So thanks everybody for all the work they've put in. There's been, of course, a lot of work behind the scenes. Stephen Lokier and Tom Kibblewhite have taken the brunt of that. And Joanna, we'd like to thank you as well very much. And we have this fantastic technical team that those giving presentations will meet in the green room. But largely work behind the scenes, but your work is hugely appreciated as well. And finally, some thanks here to our hosts, SEDS Online. We are benefiting hugely from the fact that they've now developed over a year of experience in delivering very professional meetings online. Couldn't be done without them. So thank you, SEDS Online. And thank you also to the IAS, who are sponsoring this meeting by providing prizes for the best talks each day and also the best poster. So those will be judged by members of the scientific committee and the prizes will be awarded at the end of day 2. Finally, just a little bit of housekeeping. I think most people who are speaking know that they have strict 12 minutes. If we had a Bathurst bell, we'd ring it, but it's actually more effective because we can just mute you. And that will allow 7 minutes for question and answers. We're really keen to have lots of discussion. Please post your questions into the chat, send them to everybody at the end of the talk. So once the speaker has finished, then you can post your questions. They will be read out by the session chairs. The discussion will then continue. We've got virtual tea and coffee breaks and lunch, but this meeting will not be closed at all during the day. We'll keep it open so we can foster lots of discussion. Poster presentations will be held at the end of each morning. Each presenter will have 4 minutes to introduce their poster, and then we'll move to the poster rooms for question and answers after that. I hope you've all found already that the abstracts and posters, PDF copies of all the posters, are available on the CEDS online website under the Carbonate Forum 2021. Please don't record anything. The recordings are, the presentations are being recorded. They'll be available on YouTube. And the final point is, it's up to you to find your own fire exits and your own toilets. So, you know, this is a collective responsibility meeting. I'm going to stop talking at this point because I'm really keen we try and keep it on schedule. And I'm going to pass over to the chair of the first session, which is going to be on platforms, margins and slopes, Estani and Isabella. Thank you very much.
Hi, good morning, everyone. Thanks, Fiona, for the introduction. Our first presenter today is going to be from the National Academy of Sciences, the Chinese Academy of Sciences in Beijing. Her name is Xiaoxia Huang. Hopefully I pronounce it correctly. And she will be talking about the Zhongsha atoll in South China. So welcome and go ahead.
Thank you. I just make sure you can see my screen now.
Yes.
Okay, good. Yeah, thank you very much for offering me the opportunity to present the work. I'm actually quite new face for the carbonate field, and I still feel very proud to have the privilege to work the Zhongsha atoll 2 years ago. I think Zhongsha atoll is definitely one of the most mysterious atoll system in the world, and we knew so less about it. And today I'm going to show you, it's really some first documentation of the seismic stratigraphy and the depositional signatures of Zhongsha atoll. And I'd like to acknowledge my co-authors who contributed to write this paper, which was published in Marine and Petroleum Geology in 2020. So I would like to start my talk with some general introduction of the reef types. As we know, there are 3 major reef types, including the Frisian reef, barrier reef, and atoll. Frisian reef usually composed with a reef-light and a steep slope, reef slope. And the barrier reef is different from the Frisian reef with a deep lagoon between the shore and the reef. And third type is atoll, which has usually a circular or oval shape with a deeper lagoon, open lagoon in the center, and then many atolls in the Pacific, Indian Ocean, and South China Sea. Next slide is a global distribution of the coral reefs atoll, and we can see that those reefs are mostly located in the subtropical and tropical regions. South China Sea has those 3 main reef types, really, which make it as perfect location to study the reefs. And this is the left figure is the distribution of the carbonate platforms at atolls in the South China Sea. Our study region, Zhongsha Island, is located in the northwest part of South China Sea. it's quite close to the Xiaoxia Island, but Xiaoxia Island is much more exploited with exploration wells and lots of seismic lines cross it. But Zhongsha, we don't know so much about it. And Zhongsha and Xiaoxia are, from tectonic point of view, are recognized as two rigid continental blocks which rifted out from South China Block during the late Cretaceous to the early Oligocene time, which make us believe that these two blocks probably share a lot of similarities. So I use multi-channel seismic reflection data and deep drilling wells and multi-beam bathymetry data and try to answer the following questions about the morphology of the Zhongsha atoll and the seismic characteristics and the depositional signature of this atoll. And at the end, we proposed a concept sketch of Zhongsha atoll evolution based on the data and interpretation. And the red figure shows where my four seismic lines are. And because we don't have direct drilling at Zhongsha Island, we have to take the reference with the wells from the Xiaoxia Island. They are about 200 kilometers away, which is also separated by a Zhongsha-Xiaoxia trough. So now comes the first part of my result, the geomorphology. So like the other atoll in the world, Zhongsha atoll is a ring-shaped, elongated joint atoll. It is quite large, covers over 23,500 square kilometers, and the length is about 150 kilometers from south to the north, and the width is about 75 kilometers. And the atoll system seems the age is dominated by lots of canyons and gullies. And the bathymetry data also recounted a complex system of this submerged atoll with a very shallow measured water depths, about 10 to 20 meters inside of the atoll. And the atoll shows generally very steep gradient, especially the southern part and the east part. As you can see, that the slope gradient is up to 90 degrees, and they are dominated by gullies, channels, and slumps. Now comes to the seismic interpretation part. As mentioned, we use the reference of the wells from the Xiaoxia Island and try to suggest a possible age for the sediment succession above the Zhongsha block. So we identified 6 seismic units from over 800 meters marine carbonate succession. And we found the earliest deposition occurred during the early Eocene. And we also newly discovered a rifted basin in the southern east part of the Zhongsha Island. And the 6 seismic units are clearly visible in this rifted basin. Now comes to my most favorite seismic image, which crossed the northern part of the Zhongsha atoll. It's not only has really good resolution, it really contains the key component of the atoll system. For example, the reef rings, lagoons, and Pinnacle Riffs. And we can see that the reef rings includes the lagoon and recognize on a positive relief. And the width is changing between 3 to 6 kilometers. And I'd like to zoom in the reef rim and to show you a little bit the detailed internal structure of the reef rim for the next slide. And you can see that there's a very clear boundary which marked abrupt seismic reflection changes from the below and above. And we interpreted this key boundary as a T50, which represent our middle Miocene age. And we think that below this boundary here is a pre-existing carbonate platform. And after the middle Miocene, our atoll system formed in Zhongsha Island. So we suggest that there's a crucial turning point happened at T50, and which marked the drawing of the carbonate platform or the termination of the carbonate platform and the onset of the reefs and extensive lagoons that develop. And there are more examples about the Pinnacle Riffs, and we can see from the seismic images, most of the Pinnacle Riffs, they appeared after T50, which is the middle Miocene. And there's also lots of normal faults can be observed in some of seismic images, but in general, all those Pinnacle Riffs, or most of them, actually appeared during the post-rift phase. Based on the seismic data and also our interpretation, we suggested a systematic relationship of the carbonate platform and atoll at Zhongsha Island. So at late Eocene, there's the earliest lagoon developed. If you remember that I mentioned at the very beginning, there was a rifted basin was discovered here based on our seismic. And then there's at the early Miocene, the island was more or less covered by the carbonate platforms, and some small lagoons also can be observed. And in the middle Miocene, there is a turning point that the carbonate platform was joined or shrinked, and more intensive lagoon and atoll systems start to form. And in the early Pliocene, the carbonate platform completely disappeared, and the region was dominated by our atoll system. So at the end, based on our data and interpretation, we proposed a concept sketch for the Zhongsha atoll evolution. For a bigger framework, there are two phases from the steam rift to the post-rift, and in detail, there are 6 case stages are suggested. From late Eocene to late Oligocene, it's a rifting process. There's the early rifting basins and some shallow marine sediment filled up. And in the early Miocene, the region is covered intensively by the carbonate platforms. And then comes to the middle Miocene, the turning point, and the carbonate platforms start to join. And the atoll system was formed. Especially we can see the reef rim was developing above our pre-existing carbonate platform. And there's some pinnacles already can be observed. And for the late Miocene and Pliocene, according to the drillings from the Xiaoxia Island, there were 2 drawing events.
2 minutes, Xiaoxia.
Okay, for example, at 10.5 million years and 5.5 million years, because Zhongsha and Xiaoxia, they were so close to each other, and that's why we think that this drawing event associated sea level rise probably also influenced the Zhongsha atoll formation. I think they probably promoted the atoll formation. Yeah, that's I have to say that all our results actually more or less purely based on the 4 seismic images, which left, of course, lots of unknown space for the future investigation. Now I finished my talk, and thank you. This is just the figures of the institute I'm working currently, which is located southern part of China. It's a very beautiful place to be. Thank you.
Thanks, Xiaoxia. Very interesting talk. While we wait for further questions from the attendants, I'd like to know if are there any plans to acquire 3D seismic in the area or drill wells to gather more data, or just for prospective?
Currently, I think I will go back to our map. So currently there are more going on for sure. I think I mean, for Zhongsha Island, which cross the island, probably they are the only lines, but there are more seismic lines was newly acquired around the Zhongsha atoll, for example, especially at this trough, as far as I know.
Okay, thank you. I don't see. Okay, there's a few. Let me see. We have a question if the early Miocene carbonate was overlaid by lagunal carbonate. So why was it called a drowning event?
Well, I have to see that from the seismic data, you don't really recognize this drowning information. What I observed is, I believe this is a pre-existing carbonate platform. It was joined. This is also, let me go back a little bit, my background. So I think this is also fit for a general framework of the development of the atolls and carbonate platform in the South China Sea. Of course, this is an example from Southeast China Sea, which you can also see that the peak of the carbonate or the maximum of carbonate platforms actually stopped at the middle Miocene. So I think that our result is not really conflict with the existing studies. And meanwhile, why the carbonate platform joined in the middle Miocene, it's probably because of the sea level rise. I think those side effects support our statement.
Thank you. We have another question. It says that there is a lot of work that shows that the Xiaoxia Islands have an incredibly high subsidence rate during the Miocene. Do you see similar evidence in your study area? How do you decouple the impact of sea level rise versus subsidence in your study?
I think this, I have to see there are many information or the work carried in Zhongsha Island have to take the reference from the Xiaoxia Island because there's no drilling, nothing. But I do believe that Zhongsha Island also experienced at least continuous subsidence from the early Miocene to the middle Miocene, which created accommodation space that allows the carbonate deposition.
Thank you. We have another question. Again, regarding the drowning of the platform. It says that it doesn't look like the platform was fully drowned, since there are some parts that are still carbonate being accumulated. So do you think it's really correct to refer to these surfaces as drowning surfaces?
I will not see that it's completely joined, but at least partially joined, because we don't really, after the middle Miocene, there's no obvious carbonate platforms. It's just the reef rings, lagoons and Pinnacle Riffs, which are a key component of the atoll system. So that make me believe that the Zhongsha carbonate platforms are joined or were joined during the middle Miocene, at least partially, like what I marked here. I do believe in the early Pliocene, the carbonate platform was completely joined, but probably in the middle Miocene, it's just partially joined.
Thank you. Remember, everyone hearing, you need to enter the questions for everyone so we can see it and read it out loud. There's another question if you've been able to correlate high order sea level curves to the carbonate platform drowning. You discussed this a little bit with another area, but for like general sea level curves, were you able?
I mean, for the sea level curves, I probably only see a global. Oops. I had a look. Oh, I do look at some sea level changes from the northern part of South China Sea. But I have to see that this is I'm dealing with a very small region. Compare like global sea level changes or the entire South China Sea level changes. There's not a really good match for this region. But I can see that in general, for example, at the middle Miocene, there's a sea level rise, especially because there was a middle Miocene climatic optimum and lots of ice sheet was melted. And I think those, they do have a sea level rise. And which since it's fluctuating anyway, it's difficult to see that from a larger time interval, the sea level will keep rising.
We're going to do the last one. They're asking, how do you age the Carbonate platform? I know you did correlations. Were you happy with the correlations you were able to draw between this atoll and the surrounding areas?
I think I'm pretty self-confident with my middle Miocene. I'm really look forward to the future drilling will happen here to test this, because I do believe I found the boundary which clearly shows the drawing of the Carbonate platform. And there are lots of studies from other regions of South China Sea basically also agreed that the Carbonate platform joint or at least shrink it during the middle Miocene. So I think this is probably our evidence that shows the drawing of the Carbonate platform, and it's probably also represent the middle Miocene. Yeah, I really look forward to the future drilling to test.
Thank you very much.
Thank you.
Okay, thanks for all the questions. Really nice presentation. So I'm not sure if do I need to move to the green room now? I don't know if there are any admins.
So I just stop sharing.
Yeah.
First. Yeah.
And can you stop sharing your video as well?
Okay, still not yet.
Okay, our next presenter is Alexander Petrovic from the King Abdullah University of Science and Technology in Saudi Arabia. We're going to continue with the topic of dropping carbonate systems with an example from the Red Sea margins. I don't know if Alexander is here.
Yeah, I'm here.
Ah, great.
Right, many thanks for the kind introduction, and good morning everybody, also from here from Saudi Arabia. And now we're going from the South China Sea to the other part of the planet, to the Red Sea, to our backyard. And in this talk, I'd like to introduce a new concept of carbonate platform drowning based on observations we made in the Red Sea. But before I talk about our concept and the observations, let me give you a first introduction about the Red Sea. So the Red Sea is located between Africa and the Arabian Peninsula, and it is a semi-enclosed elongated sea. It's situated in the African Arabian desert belt. Therefore, we are facing here an arid to semi-arid climate, and as a consequence, we have almost no river discharge into the Red Sea. Overall, the Red Sea is characterized as an oligotrophic environment. It's a tropical sea, and maybe as some of you know, it's very famous for its coral reefs, especially on the Egyptian side, but we have also beautiful coral reefs on the Saudi Arabian side. Talking a little bit about the basin themselves. So tectonically, the Red Sea basin is one of the youngest ocean basins of our planet. The first rifting started in the Oligocene, and we have the second important rifting phase during the Miocene. Therefore, the subsurface is characterized as a rift basin, typically with horsts and rotated tilted fault blocks. And since similar to the Mediterranean Sea, the Red Sea also experienced the Messinian crisis, we can find in the subsurface thick evaporitic successions with a maximum thickness of 2 to 4 kilometers. And in combination with the overall rift setting, the Red Sea basin is also characterized as an extensive salt tectonic environment. And last but not least, in the central part of the Red Sea, we can find salt flows sitting on the sea floor, which are related to diaparism and to the Messinian evaporites. And these salt flows are very well studied by our colleagues from the University of Manchester, as well as from the Geomar Research Center in northern Germany. So the data I will present, or the study area, is here located in the northeastern Red Sea on the side of Saudi Arabia. So here for now, let's say for almost 2.5 years, we're studying there the so-called Al-Wash carbonate platform. This is a land-attached carbonate platform, which is almost totally enclosed by a beautiful coral reef belt. And our main research was in the last 2 years, we investigated mainly the lateral sediment distribution in the Al-Wash lagoon and the controlling mechanisms. And since autumn last year, we also started to investigate the surrounding slope and the deep sea basins of the platform. So what you can see here on the right side is a high resolution bathymetry data set. So the shallow bathymetry, that means from 0 meter red down to -80 meter violet, has a resolution of 5 to 5 meter, while everything below -80 meter water depths, here in the gray, down to 1.8 kilometer, has a resolution of 30 to 30 meter. And yeah, well, what can I say? Always when I see this data, they are quite amazing and spectacular. And what you can find there is here on the western side. So here you can see the north arrow. Here on the western side of the platform, we have a deep incised canyon systems. We found also canyon systems south of the Al-Wash platform. But what we also can see are salt extrusions, which are already described for the central Red Sea, but so far never described for the northern Red Sea. And you can see here different salt extrusions or salt flows sitting on the seafloor. But what you also can find are these small, isolated, detached, sometimes etched carbonate platforms. And although we are in a perfect environment for coral growth, and we have this Al-Wash carbonate platform in the north, which shows beautiful coral reefs, these isolated platforms are at least partially situated below 40 meter water depths. So we were wondering, okay, why is it the case in the Red Sea? Because we were expecting that all the reefs are able to keep up with the rising sea level. Let's zoom in a little bit. So again, we have here the north arrow, and here you can see the southern part of the Al-Wash carbonate platform. So we identified in the south 3 sedimentary basins, here marked by B1, B2, and B3. You can see these isolated or sometimes detached or rarely still attached carbonate platforms. And the slope of these platforms can reach a height of 650 meters. And as a comparison, I plotted in here the Empire State Building, and we have slope angles up to 80 degrees on these isolated platforms. But what you also can see are here, again, marked by the yellow dashed line. You can see these beautiful salt flows here coming out of the subsurface. But they are not only famous, you cannot only find them in the Red Sea, so in marine environment, you can also find them on land. And the most famous examples are the salt flows that you can find in the Zagros Mountains, where the salt flows are coming out of these anticlines. And you can see it here on the left side. All right, let's change the view. Now we're going from 3D to a top view. So again, here we have in the upper right part, we have the north arrow. We have here with a white dashed line marked the southern margin of the Al-Wash carbonate platform. And again, we see these 3 sedimentary basins, B1 to B3. And what I would like to point out here on this image is this overall setup of basin and salt extrusion. So we have salt extrusion, basin, and salt extrusion. And when you talk to our colleagues from the salt tectonic community, or when you go in the literature, this setup of basins and salt extrusions is very, very typical for external salt tectonic environments. And you can find them, for instance, offshore Brazil, or also on the Golden Margin in the Atlantic. And what does it mean? Well, it means that we have in the subsurface and salt displacement towards the basin center. Okay, but let's focus a little bit on this area where we have these isolated carbonate platforms, which are situated in quite deep water depths for a shallow water environment. So when we have now a look on this bathymetry data, first of all, well, these isolated or these individual carbonate platforms have a quite interesting shape, but I'd like to bring your attention, first of all, to two specific features. So the first one is located here in the northern part, and you can see here a close-up on the right side, and it looks a little bit like, yeah, well, we have half circle structures, right? And it looks a little bit like an ice cream scoop. So we interpret this as a consequence of listric faults overgrown by coral reefs, and in a sec I explain our interpretation. What I also like to point out here, or to show you, are these very interesting features here in the slope that we found in water depths around 300 to 350 meters, which we interpret as creeping. So why we interpret these features here in the north as listric faults and here with creeping? Well, in combination with the fact that we have here on the southern part of this slope, where these isolated or these individual platforms are sitting on top, we have a salt flow coming out of the slope. And again, when you talk to our colleagues from the salt community, that's not untypical for extensional salt tectonic environments. And they call this feature or this overall setup salt canopy thrusting. So what's happening? We have a salt diapir coming up from the subsurface, but instead going straight through the seafloor, it's leaving the subsurface on the side, here in our case on the side of the slope. And related, or because of the salt displacement or the salt withdrawal, on the roof of this salt diapir, we generate lithic faults, and the overlying sediments, so the roof starts also to rafting towards in the same direction like the salt is flowing. So that means we have here an overall salt displacement or a movement towards the south. So when we now combine the different movements, that means we have an overall setup of an extensional salt tectonic environment towards the basin axis of the Red Sea, towards, so the, yeah, let's say the west. And we have this more localized movement here related to the specific features towards the south. So, and I mean, when you look on these isolated platforms, you can see they look, or they give us the impression they look like in dispersed puzzle pieces. So when we now do a small experiment and we digitize these individual platforms and we're saying, well, we try to move them together related to the opposite movement. So you can see, well, it fits not bad together, right? Not perfectly, but it fits in a way together. All right, but let's have now a closer look on these individual platform here with a very interesting shape. And I do not have the time to discuss the shape more in detail into this talk. But what I like to point out here is the carbonate system themselves. So when you go in water depths here in the, so, well, let me start again. So here in the south, almost we've seen more, yeah, we have shallow water depth. That means we have here, we can find here more healthy coral reefs. While when we're going to the south, the water depth is increasing. And when we have a look here on the carbonate system, what we see is that in deeper water depth, starting between 35 and 38 meters, we can almost find no shallow water corals anymore. But what we can find are red algae sponges. We can also find here in 60-meter water depths, totally drowned reef structures, and in 90-meter water depths, so this is here in this small depression, we can only find red algae. All right, so when we now summarize our observations, so, well, I showed you that the southern awash platform margins were strongly indications for external salt tectonic. Well, we are an overall extension salt tectonic environment, so that's obvious in a way. I also showed you indications for a margin collapse, so that the margin of the south awash platform margin collapsed, and that it looks like that individual platform pieces are rafting towards the basin center. And
2 minutes, Alex.
Thank you. And the major parts of the rafted platform pieces are situated below 40-meter water depths. So we think that in this case that the collapse, the rafting, and the drowning of these carbonate platforms is related to salt displacement. And based on our observations, we developed a concept. So starting here on top with an initial stage, we have a thick salt layer below, we have siliciclastics deposits above, and on top we have already a developed carbonate platform. But at a specific point, when the overburden pressure was too high, the salt started to move, and the southern margin of the awash platform started to collapse. And based on that parts of these carbonate platforms, of these now isolated platforms, individual platform pieces, were situated in deeper water depths, and due to the slight higher subsidence rates related to the displacement of the salt, the carbonate platforms at least partially started to drown. All right, I'm looking forward to a good discussion, and thank you very much.
Thank you very much. It was a really nice talk, really nice images. I really don't know the area, so have you ruled out any influence of volcanics in sustaining this small carbonate platform for mounts there?
So there's no direct volcanic activity in this area. So you have on the basin axis themselves, there you have volcanic activity because it's a young mid-ocean ridge here. So we have submarine volcanism, and you have in the hinterland, on the Arabian Shield, you have volcanic activity. But in this specific area, there's no volcanic area so far observed.
Thank you very much. Let's see, I'm going to start reading a few questions. As always, a key question is, aside from rapid relative sea level rise, in this case, perhaps due to salt tectonics, what other processes could reduce carbonate accumulation rate enough to drive this apparent drowning? For example, water temperature, salinity, etc. What are your thoughts?
Well, yeah, well, that's a good point. I mean, in comparison to the other oceans, the Red Sea has a much higher salinity, and also the temperature is much higher than compared to the Atlantic, Pacific, or the Indian Ocean, right? So it was always a special environment. So I think temperature, salinity changes maybe not the main issue. Of course, they can play a role. I mean, at the end, it's then a chicken and egg question, right? What was first? So do we at first the salt displacement? So the carbonate platform went down, and because of that, everything was a little bit well located in slightly deeper water depths. So, for instance, sediment was easier for sediment to settle down, and corals do not like sediments, you know. So I mean, there are different opportunities who can increase this effect, but I think the overall mechanism is the tectonic who drives the drowning of the platforms.
Thanks. We have another one. Do you know what prompted the onset of salt movement? It was just a platform failure, or I don't know.
Yeah, that's a good question. Yeah, we started to discuss about this, but based on the fact that we do not have seismic data at the moment, so we're planning to shoot some seismic lines, which, can you imagine, it's not quite easy in Saudi Arabia, but we're planning to do this. I think then we have more answers to these questions, but it could be related, I don't know, that's after the Messinian crisis and the development of the Pliocene fan deltas on top of the salt, and let's say the Red Sea started to get flooded again. Maybe this big volume of seawater on top, maybe that gave the initial, you know, click for the salt displacement. Good question. At the moment, I have not a straight answer. I'm sorry.
Are there any sign of incipient rafting on the main platform?
Yeah, and you mean on the main? I think the question is focused on the main.
I guess, yeah, it's from the attach.
Yeah, so we found some indications that the platform themselves is also rafting, but it's still under investigation. But there are indications. But due to the massive coral growth, again, without seismic data, it's very, very hard to tell. But it looks like, let's say.
I don't see any further questions. Well, thank you very much for the presentation again. Thank you for all the questions.
Yeah.
Now we're gonna, well, Isabella is gonna present the next talk. So are you there? Yes.
I'm here. Okay,
right.
Hi everyone. So I have now the pleasure to introduce our next presenter, which is Selin Coskun. Selin is a PhD candidate at Manchester University, and she will tell us a bit about margin collapse in a Cretaceous carbonate platform located in the offshore of Senegal. So Selin, you can, if you're there, you can share. Hi, Selin.
Hi, Isabella.
Hi. Okay.
So can you see my screen right now?
I can. And
Okay.
yeah, go ahead. You have 12 minutes. Thank you.
Great. Thank you for the introduction. So today I will present to you the Cretaceous evolution of long-lived carbonate platform offshore Senegal, Northwest Africa. So I just finished my first year on my ongoing PhD. So this is the preliminary results of my ongoing PhD study. So why we have a research on that area? Because the carbonate platform on my study area is dominated by large amphitheater-like structures. And those structures are cited by many authors in many modern carbonate environments, such as Florida and Bahamas. They're really important to understand the evolution of the carbonate platforms. And of course, it's crucial to understand the possible triggering mechanism for this margin failure. And scallop margins will have their related gravity collapse deposits, and they may form important hydrocarbon reservoirs, such as the one in the Poza Rica field in Mexico. So why this research is significant? Because these features have never been identified in the offshore Senegal before, and they reveal important aspects about the carbonate platform evolution. And they may form a new hydrocarbon play within the already productive MSGBC basin. The term scallop margin is first mentioned in Mullins and Hine's paper in 1989. They described those structures as large, irregular, convex bankward embayments. And they speculated that the small isolated Bahama banks may be erosional remnant of once larger platform. And as well as the Bahama, we have a couple of examples from southeastern China, for example, the Triassic age Yangtze platform. You can see those amphitheater-like structures here. Holocene age Great Barrier Reef. So we still have this amphitheater-like structures. And we have another example from West Florida, the Miocene age carbonate platform. You can clearly see those scallops on the margin. So my study area is located in the Senegal basin. So it's an Atlantic type passive margin, and it's subdivided in three smaller basins. And my study area is located in the southern parts in the Casamance sub-basin here. And the rifting it started in this part during Jurassic. And during the post-rift stage, we have an important event related to this scallop margins. It's the shift from carbonate to siliciclastic at the end of the Aptian stage. So here on the right-hand side, you see the seismic section from my study area. The orange horizon is the top carbonate horizon. It's the late Aptian age. And this shift is related to the opening of the equatorial Atlantic and related to the global sea level fall mentioned by Huck during the latest Aptian time. So when we mapped the carbonate top on my study area, we identified 4 scallop margins. The first one is located in the north, and the other 3 ones are located in the southern part of the study area. They are steeper when compared with the escarpment margin of the platform, and their width vary from 9 kilometers to 12 kilometers in that area. Of course, each scallop margin will have its collapse deposits deposited either on the slope or in the basin. How we see those breccia in seismic sections. So usually they present itself as a chaotic, low to moderate amplitude seismic reflections. And here we see a south-north section from the 4th scallop margin. we have this low angle platform, and we have this collapse platform here, and you can see its scar clearly. And we have this paleo canyon related to this collapse platform. On the seismic, we identified a first episode of collapse about like 10 kilometers long. And we identified another episode of collapse here, which is about 4 kilometers long. And all the Cenomanian sediments are onlapping onto this second and first episodes of collapse. So how they are distributed, how the collapse deposits are distributed in the study area. So to reveal this, we ran a RMS amplitude map, RMS amplitude attribute. So basically what we have done is, so basically what RMS show us, the lithology change. The lithology change, the lithology change shows itself as higher RMS amplitude because of the chaotic nature of the collapse deposits. Here you see mostly the high amplitude values are located near the scallop margins. And when we have a wide slope, the collapse deposits are located on the slope only. We don't have any deposition on the basin, in the basin. But when we have a narrower slope, we have the deposition on the slope, on the toe of slope here and in the basin. So what might cause the scallop margin formation? So many authors mentioned many triggers for this scallop margin formation, from gas charging to high relic pore pressure, but now I'll focus on the tectonic, subaerial exposure, and gravitational compaction. So in order to evaluate the tectonic effect in my study area, I compared two different study areas. So the first one is from Max Kessen's PhD study, and it's located in the northern part of my study area here. And the top carbonate, the latest Aptian age top carbonate, is dominated by canyon and channel couples in that area. But in my area, the top carbonate horizon is dominated by this amphitheater-like structure, which indicate the margin of the collapse of the margin. If we now evaluate the fault and fractures distribution in the in both areas, the study area located in the north has more of a local moderate amplitude. It's east-west lineations, but whereas my area has some more continuous high amplitude east-west discontinuities. So this shows that my study area's platform margin is much more faulted than to this study area located in the northern parts. Another possible mechanism could be sea level change, because as I mentioned before, Huck mentioned the prominent sea level fall during at the latest Albion time, and this sea level fall revealed itself as the presence of paleokarst in my area. So on this top carbonate horizon, we can see some sac features on seismic, which indicate the presence of paleokarst. And in the variance attribute, the paleokarst show itself as karst troughs, and they cover a total area of 70 kilometers square. So another possible mechanism could be the sediment loading, gravitational compaction. So during the latest Albion, Aptian, we have the sea level fall, so the exposure of the carbonate platform. And after that, we have the deposition of the progradating Albion clastics on the shelf. So this sediment loading might be creating might be increasing the compaction of the platform sediments, and this will lead to the pore pressure increase, which might lead to the collapse. So based on our seismic interpretation, we proposed a conceptual 2D model. So from Jurassic to late Aptian, during the passive margin stage, we have the aggradation of the platform. We call it aggradational because we don't see any indication of the progradation. They are either non-existent or eroded.
2 minutes, Selin.
Okay, thank you. From the late Aptian to early Albian, we have the sea level fall, we have the platform exposure and erosion and bypass of the platform. We have the deposition of the Albian slope and basin fan. We have the first episode of margin collapse triggered by the sea level fall. And we have the breccia deposition on the slope. And we have the landward retreat of the margin escarpment. And from the early Albian to late Aptian, we have the sea level rise, deposition of the Albian ice condensed section, and deposition of the Albian progradating delta on the shelf. And we have another margin collapse triggered by this sediment loading here. And we have another breccia deposition and another landward retreat of the margin escarpment. So to sum up, we identified 4 scallop margins in the study area. The carbonate platform in Senegal is dominated by collapse structures and their related collapse deposits. When we compare my study area with another study area located in the north, our study area shows more continuous discontinuities, indicating more faulted margins. And the presence of paleocars indicates a subaerial exposure during the late Aptian, early Albian time, and possible triggering mechanism for the formation of scallop margin in Senegal basin are tectonics, global sea level fall, and gravitational compaction. Thank you for listening to me.
Thank you, Selin, for the great presentation. I have just a quick curiosity for me, then we can see if you have any question in the chat. Are you planning to use any other data to address your research question, such as well data, maybe coarse, maybe not from the other, maybe from an analog?
To be honest, I don't have any well control in my study area, Isabella. So that's why my first step will be to get as many information as possible from seismic. But I have a couple of exploration wells located in the northern part. So I can maybe correlate those wells and then compare the lithological information and hopefully transfer those information to my area.
Great, thank you. Okay, so I see that we have a question in the chat, a question from Jim. Very nice talk, thank you. What do you think is the origin of the narrow carbonate ridge in the southern study area?
Okay, so I think the possible mechanism for this carbonate ridge formation is the reactivation of the fracture zones during the opening of the equatorial Atlantic, because during the latest Aptian, early Albian time, we have the opening of the equatorial Atlantic, and this caused the transpressional regime as a result of the reactivation of the fracture zones here. So that's why I think that this carbonate ridge is caused by the tectonic in the area.
Thank you, Selin. We have a comment or maybe it's a question from Eugenia. Such a shape of the collapse is circular, most likely indicative of paleokarst. I think this is more of a comment than a question, but if that's a question, maybe Eugenia, you can clarify.
To be honest, I couldn't understand the circular shape on this 2D map or circular shape So for example, those circular shapes.
She wrote yes here.
Yeah, for example, they might be paleokarst, or they might be some fluid escape structures as well, because I don't have any seismic section to show that, but we see on the seismic section that the sag on seismic reflections are continuous from the Albian to the Jurassic section.
Thank you, Selin. We have another question from Peter. Great talk and wonderful data. You have got evidence of the data for RSL fall, relative sea level fall. So does referencing a speculative model of global sea level really had anything important? Global sea level curves are too problematic to be really useful in this way for many reasons.
Yes, I agree that global sea level curves might be sometimes problematic, but maybe my next step, actually not maybe, but one of my next step will be to create a relative sea level curve from my data once I can have the depth control from the seismic depth conversion.
Okay. Then we have just a comment from Ismail, which is writing, thank you for the great talk and congratulations.
Thank you.
At the moment, we do not have any other question. We can wait a second, see if someone came up with a question. Okay, another comment here. A circular scallop shape is a fairly normal pattern, not related to karst. Hill collapse will have the same shape. Maybe do you want to comment on this, Selin?
Yeah. Okay, so yes, they are not. I mean, this scallop, this circular shape are not related to paleocaps, but margin failure. But here on the seismic section, sorry. Yeah, here, this sag features. So this is where we interpreted them as karst. And because they reveal, we have a karst trough located in the middle of this prominent structure on the south.
Okay, thank you. So we have another comment. To me, this is a normal slope and platform margin adjustment process. I guess you have, thanks for the reply, great talk. We have another question, again from Pete. Pete says, maybe I missed this in the talk, but do you have any evidence of rotation and tilting in the non-collapsed parts of the platform?
Not in my area. Actually, so far the only volume that I have is time volume. So sometimes it's really problematic to locate any real tilting and any real fault presence in a time volume. So what I will do as a next step, convert this data to depth, and to see if we have some real faulting and some real tilting controlling the platform. Because in the northern part of my area, some companies and some studies mention about the tilting of the platform. So yes, we should see some tilting, but I really need to wait until I get the depth volume.
Thank you, Selin. Another question from Giovanni. Great talk, Selin. Thank you. Based on your seismic data, base of slope breccias are coeval, stratigraphically correlatable, or they occur at a different stratigraphic levels?
When I performed this RMS amplitude map, actually the slope breccias are, I think, coeval, and they occur at the same stratigraphic level because we have this, and the time will be the before Cenomanian, but after the Aptian time.
Thank you, Selin. Sorry, I missed a comment, previous comment from Fiona that mentioned they do seem very large for karst features. Do you have any comment on this?
Which features? I mean, those are not karst. Okay, so those are not karst features because they're about, like, as you said, Fiona, they are more than about like 10 kilometers wide. But if you mention those features,
Fiona mentioned, sorry, the ones that you were discussing earlier to the south.
Okay, so I think those ones here.
Yes.
Okay,
yes.
Yeah. What I'm thinking about those structures, so they're mostly, they could be fluid escape structures, so not paleokarst.
Thank you, Selin.
Mm-hmm.
Okay, we have another comment from Eugenia. The age of platform is Jurassic, isn't it? And then you have an unconformity with Aptian, big gap paleokarst.
The platform age is from Jurassic to Aptian, and we have the okay. So we have. I'll show you a. I have. No, I don't have here, but so the platform age is from Jurassic to late Aptian, and we see the paleokarst on the top of this Aptian age carbonates.
Thank you, Selin. If you look in the chat, you have been suggested with a paper about large collapse without karst.
Right.
You may want to look at that. Okay. I encourage. I think we. Sorry. Yeah. I'm not sure if you're still waiting for our next speaker. If we do, I encourage you to write more question or comment so we can keep going with the discussion until the next speaker will be with us in the room, if it's not already. Oh, Jesus, I can see you. Okay. Selin, thank you very much for the great presentation and especially for the great discussion afterwards. It's very much appreciated.
Thank you, Isabella.
If you can kindly stop sharing and
sure.
Stop your video. Okay. So our next presenter is Jesús Reolid. He's a postdoc at University of Granada, and he will tell us about the evolution of a Miocene carbonate infilled canyon located in the Ester Mediterranean. Jesús, I see you there. Can you unmute and start your video, please? Jesus is writing, I'm not allowed. He's not allowed to unmute or start your video, I guess.
I'm working on it.
Okay, thank you.
Okay, I think I'm finally here. I'm sorry for being a mess with.
No problem. Can you start sharing?
Yes.
Amazing. I see your presentation. And yeah, go ahead. You have 12 minutes.
Okay. So thank you for the presentation, and sorry again for the inconvenience. Today, I would like to present some really preliminary results of the next paper I'm working on with some colleagues from the University of Haifa in Israel, and also some colleagues from the University of Jaén here in Granada, where I'm based, from Spain. And the topic is about the evolution of a Miocene canyon, and especially focus on its carbonate infill in the pre-evaporitic deposits of the Eastern Mediterranean. So why the Eastern Mediterranean? When I was doing my PhD some years ago, so far, I was studying the southeast Spain outcrops, where especially I think most of the people here may know the outcrops from the Sorbas Basin, the Carbonate Reef, that is a really beautiful examples of carbonates predating the Miocene and salinity crisis. And then I meet some colleagues from Israel and say, like, oh, here we have also some carbonates that are predating the Miocene and salinity crisis. Could it be interesting to make a comparison? So study the evolution of these carbonates prior to the salinity crisis. So I say, yes. So I moved there to Israel. Really sad to hear the things we are hearing today in the news about this area, especially because the study area, so the Beersheba, is in the nearby of Beersheba, especially the topic is the Beersheba-Gaza Canyon. So here you can see outlining the trace of this Miocene canyon. Nowadays it's all covered by Miocene and Pliocene stuff. And there was a nice seismic survey. You can see plenty of seismic lines. Here down, you see a color scale of two-way travel times. So you can see that actually along the canyon is getting deeper. So I have a really impressive incision of really hundreds of meters. I'm going to be showing the northernmost part in seismic line with this, as I say, onshore survey that is, I think, was really interesting. But we also have the chance, when I was in Israel, to visit some of the outcrops. So I have 4 stations. I'm going to be focusing in 3 of these 4, especially station 2 that is in the center of the Beersheba area, but also station 1 that is in the border, so where we can see the incision of the channel, and station 4 that is one of the latest stages and one of the most interesting, as you may see later. I'm not going to enter especially in speaking about the stratigraphy or the regional stratigraphy of the area, just for you to know when we are looking on the seismics that there is a green Cretaceous formation, then Pleistocene, sorry, that's a terrible mistake, Eocene orange formation, and then we have this Oligocene, Miocene in yellow, and especially here in the upper part, you can see that is written Pattis formation, that is the infill of the channel that is going to show. So here, the first of these lines that are close to the mouth of the channel, of the canyon, actually, you may see the scale is just impressive. It's a few kilometers wide. It's a big canyon. And we can see how the Cretaceous, the Eocene, and even some early Oligocene deposits are eroded and totally truncated, the reflection associated to them. And then we have first the deposition of some beds which are mimicking the morphology of the canyon, and then chaotic reflections, what we actually see in some outcrop, even slumping, and some features which are indicative of mass transport deposits in the borders of the canyon. So the line that I show was what is called here figure 3. Now we are going to see what is figure 4, that is actually the very mouth of the canyon again. And you see here the different formation with the truncation of all the deposits which are pre-Eocene. And then here in white, this embedded shell and the patty formation with some deposits again accommodating to the shape of the canyon. This also some other chaotic reflections related to the Mastrompo deposit, but there is something that I think you should pay special attention, and it's close to the borders. In the shallower part of the canyon, you can see some reflections. I hope you can see my mouse. You can see some reflections which are actually clinoform bodies. And actually, in some of them, there is not only the clinoform, but it seems to have an edge that could be a reef. Something really similar is what we see in South Spain, in the Sorbas Basin. So here you see this picture from an old publication that we have one of these reefs, what is forming an edge with the platform, and then these clinoform bodies, which are actually the same age as that we are seeing in Israel. So then we have a look on the field. So first I'm going to show this station that I said is the first one for showing the incision, and here we see the Isabella group, these Eocene deposits that were eroded. And you see how there is a big change here from white to reddish. You can also see here down a change from a chalk to something more grainy, and that grainy thing is actually a breccia out of the exposed margin of the canyon. So it's really evidence of this canyon incision. So here we have like the oldest deposits. When we go towards the northwest, we are more into the channel that is station 2 in the center of Beersheba. This is the city that gives name to the channel, and here we have a huge outcrop is a quarry in the middle of the city, and we can see 3 different units. So first we see this one here in the lower part. You can see these clinoforms that are dipping toward the south-southwest, so it's actually dipping toward the canyon interior. We have also channels here in orange, which are cross-cutting these clinoforms, and these channels are parallel to the main axis of the canyon, so are also flowing toward northwest direction. And then on top, when the accommodation space was filling up or partially filled, then we start to have some sub-horizontal beds, which are not as calcarenitic as in the clinoform body, but give an appearance more nodular. So it's a nodular limestone with abundant trace fossils. So here, just a closer look to see how these channels within the canyon are also huge, are of several tens of meters, and they are cross-cutting this unit with clinoform bodies. We have this big truncation of the clinoforms, and we can find even big blocks. So there is an abrupt change in phases from fine-grained, well-laminate calcarenites to calcigrudites or breccia in the canyon infill. So here you can see this abrupt contact. It's really obvious when you're in the field. And the latest station, so we have seen so far station 1 and station 2. And then I go to station 4. Why? Because I think it was really interesting. We found corals, actually corals which look really similar to those we found in southern Spain, from also the same age, from the Miocene. So we found the corals, but not only the corals. I mean, coral could be interesting, but it's actually a reef that is formed by the combination of corals and a thick stromatolitic crust. You see this thick stromatolitic crust was early consolidated because the stromatolites have abundant lithophaga borings. Which kind of species? There are different species of corals, but some of them are these poraites, which are really, really interesting because it's exactly the same thing that we find in South Spain, but also in the northern part of Morocco, also in Mallorca. These poraites and stromatolite reefs are really, really distinctive from the upper Miocene, from the Miocene, are the last big reefs that occurred before the Messinian salinity crisis. So it was really interesting to see that some in the western part and some in the eastern part are exactly the same. You cannot distinguish one's hand sample to another one. So just for concluding, we can make a short discuss about the evolution of these canyons. So first of all, we have the incision that is cross-cutting all these Eocene and previous deposits, and during this first incision phase, we have abundant mass transport deposits coming from the flanks toward the canyon interior. Then we have a second phase of development, so we have the partial infill because we have in situ carbonate production, because we can see that in the component, but also export from the sides of the canyon, because we still see some influences of mass transport deposit, but also currents along the canyon, because we saw these channels parallel to the main canyon axis, as we see in station 2. And the later stage, when the canyon was partially or almost completely infilled, that it was actually acting more like an embayment than an actual canyon, because of the development of this reef system that was progressing toward the platform interior. We know because we saw these carbonate reefs in the outcrop, but also because of the imaging in the seismics. And finally, all this was infilled with the post-evaporitic part of the substation. We have Pliocene, and then the shoreline was moving all the way to the northwest, where it is nowadays. And that is mostly the conclusion we have so far. Now we are trying to connect this information with global sea level curve and with tectonics analysis, but that will be our next step. And before concluding, I want to thank all the universities which are support the different, for my investigation and that of my colleagues, but also the CAUST, the European Cooperation in Science and Technology, because found this research to 2 actions in 2019 and 2020. And that's all from my side. Thank you.
Thank you, Jesus, for the amazing presentation. It was very interesting. While we wait for questions in the chat, just a quick curiosity from me. Are you aware of any system where these channels in fields bears significant hydrocarbon resources?
Well, no, to be honest, that it's been really challenging to understand these channels within the main canyon. It's something that it's what we are currently working, because they are all in different depths within the flanks of the canyon, and with different widths. So we do not totally understand what is the process. In any case, it could be interesting because they have really a large grain size, so it could be a nice, I don't know, trap. But the point is that we need a seal on top, and on top the only thing that we have, I mean, there is no any deep environment, something like clays of Mars that could seal it. So the only thing we have is this nodular calcarenite that is actually really porous. We have a lot of bioturbation, so probably no chance to find any source of hydrocarbon there.
Thank you, Jesus. Still waiting for question. And yeah, just another small. I understand what you mean, but anywhere else in the world, is there any place where this type of systems actually have hydrocarbon reservoir?
Well, it's kind of famous. I know that in Saudi Arabia, on these channels, they found beautiful sources, and actually there are several analogs here also in southern Spain. They are not equivalent, I mean, they are not carbonates, they are in stratigraphy, but they are studying similar canyon system with these tributary channels, and they are using for modeling the hydrocarbons outcrop or in somewhere. Yeah, sorry.
Thank you, Jesus. Very interesting. Okay, a question from Lillian. Could the inclined strata be interpreted as lateral accreting filling?
Well, actually, there are both things. So in the case of the uppermost part of the Pattis formation that is showing the seismic lines, and also with the reefs, I think it's clear that it's just progradation by this reef, no, when it moves toward the canyon interior. But I think it's true that in the case of the middle part of the canyon, so when I show this clanophone in this 3D photogrammetric model, they were in green. That is probably just accretion. So we have accumulation of this mass transport and probably part of in situ or almost no, so parautochthonous accumulation of carbonate that they were just prograding as in a normal channel, but in larger scale.
Thank you. A question from Roberto. Hi, Jesus. Your talk is really interesting. Have you estimated the depth in which the channels formed?
Well, according to the paleobathymetry, it should not be so deep. And actually, inside the channel, we found some shallow fauna. So within this calcirudite, this breccia that I showed, there are some coral reef species. So this should not came from so far, especially because we found some blocks which are up to 1 meter inside. So even when we are considering that that could be export from the canyon flanks, looking at the present day topography, the canyon flank could not be much higher than a few meters. So I think they were really, really shallow. But I cannot say anything else or something more precise.
Thank you, Jesus. There is another question, but I guess we need to join the discussion room. Okay.
Absolutely.